Actually, the linear congruence. So we can solve the linear congruence in many methods. So here we are able to solve the system of linear congruence by using Wilson's theorem, Fermat's Little theorem, and Euler's 5 functions. Then statement of Little's Fermat theorem is, let P be a prime and A be any integer such that P does not divide A, then A to the power P minus 1 is congruent to 1 mod P. Then we discussed the applications of Fermat's Little theorem. So after discussing Wilson's and Fermat's theorem, we have discussed Euler's 5 function. So the definition of Euler's 5 function is, let M be a positive integer, then Euler's 5 function, which can be represented as phi of M. Phi of M means the number of positive integers less than or equal to M and relatively prime to M. And we proved some theorems based on Euler's theorem. A positive integer P is a prime if and only if phi of P is equal to P minus 1. Then I introduced the multiplicative function. A number theoretic function f is multiplicative if f of mn is equal to f of m into f of n whenever m and n are relatively prime. So in the continuation of multiplicative function, you studied a definition. Let f be a, with lowercase f be a multiplicative function, then capital F of n is defined as summation of f of d, where d is the divisor of the given n. Then we have proved the fundamental theorem for multiplicative function. Let f be a multiplicative function and n is a positive integer with canonical decomposition. N is equal to P1 power K1 into P2 power K2 etc. PR power KR. So here n is a composite number which can be represented the product of distinct primes. Okay, that form is called canonical decomposition. So at the time f of n is equal to f of P1 power K1 into P2 power K2 etc. PR power KR. Here f is a multiplicative function, then f of n will be represented as f of P1 power K1 into f of P2 power K2 etc. f of PR power KR. So we solved the problems by using fundamental theorems for multiplicative functions. We discussed elaborately. Then Euler's 5 function. If P is prime, then Euler's 5 function phi of P will be P minus 1. Suppose P be a prime and K is any integer, then phi of P power K is equal to P power K minus P power K minus 1 or P power K into 1 minus 1 by P. Then phi of n. Here n is given in the canonical decomposition. That means n is equal to P1 power K1 into P2 power K2 etc. Pt power Kt. At the time Euler's 5 function of n is equal to n into 1 minus 1 by P1 into 1 minus P2 etc. 1 minus Pt. And we proved Euler's 5 function is multiplicative function. So which is one of the important theorem. Then we discussed tau and sigma functions. Tau of n means the number of divisors of the given n. Sigma of n means the sum of the divisors of n. Okay. And we proved tau and sigma functions are multiplicative functions, and tau of p power k is equal to k plus 1. Tau of sigma of p power k is equal to p power k plus 1 minus 1 whole divided by p minus 1. Okay. So we should be remembered. So we solved many problems by using tau and sigma functions. So in the continuation, we will see some tricky problems from Unit 5. So solve the congruence x square is congruent to 1 mod m for each modulo m. Okay. Here the first mod value is 6 and second mod value is 8. So given, so the given linear congruence x square is congruent to 1 mod the first m value can be taken as 6. So we are going to solve x square congruent to 1 mod 6. Okay, the first mod value is 6. So we are going to find the solution of the given linear congruence by trial and error method. Now put x equal to 1 in the given linear congruence. So 1 square 1. So 1 is congruent to 1 under mod 6. Okay. Then put x equal to 2. Okay. Actually here mod value is 6. Therefore x can take the values between 1 and 5. Okay. So initially I put x equal to 1. So 1 satisfies the given linear congruence. Then put x equal to 2. So 2 square. So 2 square is 4. 4 is not congruent to 1 under mod 6. Then putting x equal to 3. So 3 square, that is 9. 9 is not congruent to 1 mod 6. Now putting x equal to 4. 4 square 16. So 16 is not congruent to 1 under mod 6. Now putting x equal to 5. So 5 square 25. So obviously 25 is congruent to 1 under mod 6. Since when 25 is dividing by 6, you can get the remainder 1. So x square is congruent to 1 under mod 6, whose solutions are 1 and 5. So 1 and 5 are satisfying the given linear congruence. Okay. Then another mod value 8. Okay. So we are going to find the solution of the linear congruence x square congruent to 1 under mod 8. So again, for finding the solutions, we are applying the trial and error method. First putting x equal to 1. 1 square 1. 1 is congruent to 1 under mod 8. Okay. Then put x equal to 2. You can get 2 square 4. 4 is not congruent to 1 under mod 8. Put x equal to 3. So 3 square 9. So when 9 is dividing by the mod value 8, you can get the remainder 1. So clearly 9 is congruent to 1 under mod 8. Then next value 4. Putting x equal to 4, you can get 4 square 16. Okay. So 16 is not congruent to 1 under mod 8. Then put x equal to 5. You can, so 5 square 25. 25 is congruent to 1 under mod 8. Since 25 is dividing by 8, you can get the remainder 1. So 25 is congruent to 1 under mod 8. Then next value x equal to 7. So 6 square 36. So 36 is not congruent to 1 under mod 8. Then putting x equals 7. 7 square 49. 49 is congruent to 1 under mod 8. Since 49 is dividing by 8, you can get the remainder 1. Yes. Since 6 8s are 48, so the remainder is 1. So obviously 49 is congruent to 1 under mod 8. So here x has taken the values between 1 and 7, since here the mod value is 8. That's why x has taken the values between 1 and 7. So what are the values satisfy the given linear congruence under mod 8? 1, then 3, 5, 7. So x square is congruent to 1 under mod 8, which is having 4 solutions, 1, 3, 5 and 7. Actually finding the remainder, look at the next problem. Finding the remainder when 24 to the power 1947 is divided by 17. Actually, so the solution for this problem can be received by using Wilson's theorem. So it's Fermat's little theorem and also Euler's phi function. Okay. So any one method can be applied for getting the remainder. So in this problem, we are going to apply the Fermat's little theorem. So look at the base. So 24 to the power 1947. Here the base is 24. So 24 to the power 1947, which will be divided by 17. So the mod value will be considered as 17. The base, look at the base 24. 24 is greater than the mod value. So when 24 is dividing by the mod value 17, you can get the remainder 7. Since 117 is 17, so 24 minus 17, you can get the remainder 7. So 24 is congruent to 7 under mod 17. But we are going to divide 24 to the power 1947. Okay. So 24 is congruent to 7 mod 17, both sides increasing the power 1947. So 24 to the power 1947 is congruent to 7 to the power 1947 under mod 17. So which will be considered equation 1. Statement of Fermat's little theorem. If P does not divide A, the theorem will be A power P minus 1. A power P minus 1 is congruent to 1 under mod. Okay. If P does not divide A, then A power P minus 1 is congruent to 1 under mod P. Here the mod value P 17. Then P minus 1 will be 17 minus 1, 16. The base A is equal to 7. Since 24 is congruent to 7, therefore A will be taken as 7. Then condition will be verified. Here the condition is, so when will we apply the Fermat's little theorem? Okay, while satisfying the condition, the condition is P does not divide A. Here P is 17. So 17 does not divide 7. Okay, so condition is satisfied. So we are going to apply the Fermat's little theorem. So A power P minus 1. So 7 power 17 minus 1, that is 16. So 7 power 16 is congruent to 1 under mod 17. Okay. So now this linear equation will be considered equation 2. Now, actually look at the equation 1. 24 to the power 1947 is congruent to 7 1947. Okay. So actually we want the remainder when 24 to the power 1947 is divided by 17. But 24 to the power 1947 is congruent to 7 power 1947. Therefore, it is enough to find the remainder when 7 power 1947 is divided by 17. So therefore, 17 power 1947 is congruent to So now 1947 will be divided by 16. Will be divided by 16. You can get the quotient 121 and the remainder 11. So by division algorithm, 1941 plus 11. Okay. So therefore 7 power 16 times of 121 plus 11 under mod 17. Then 7 power 16 times of 121 can be written as 7 power 16 whole power 121 into 7 power 11 under mod 17. So look at the equation 2. Linear congruence 2. 7 power 16 is congruent to 1 under mod 17. Therefore 7 power 16 is replaced by 1. So 1 power 121 1. So 1 into 7 power 11, 7 power 11 more. So 7 power 1947 is congruent to 7 power 11 under mod 17. So which will be put equation 3. So generally 7 square. 7 square is 49. When 49 is dividing by 17, you can get the remainder minus 2. So 7 square is congruent to minus 2 under mod 17. Now 7 power 11 will be simplified. 7 power 11 is congruent to, it can be written as 7 power 10 into 7. Okay, actually 11 is equal to 10 plus 1 now. So 7 power 10 into 7. 7 power 10 can be written as, say, a power mn is equal to a power m the whole power n. So 7 power 10 is equal to 7 square the whole power 5. But 7 square is congruent to minus 2. So minus 2. So 7 square will be replaced by minus 2. So minus 2 the whole power 5. Minus 2 whole power 5 is minus 32. So minus 32 into 7 under mod 17. But minus 32. Then minus 32 is dividing by 17. You can get the remainder 2. So minus 32 is congruent to plus 2. So 2 into 7 14. So 7 power 11 is congruent to 14. Actually 7 power 11 is congruent to 7 power 1947. But 7 power 1947 is congruent to 24 to the power 1947. So therefore 24 power 1947 is congruent to 14 under mod 17. So when 24 to the power 1947 is dividing by 17, you can get the remainder 14. So just go through the problem. If you have any doubt, you can ask me. So shall I move on to the next problem? So find the remainder 199 to the power 2020 is divided by 28. So this problem can be solved by using Wilson's theorem or Fermat's-Little theorem or Euler's 5 functions theorem. So this problem can be solved and getting the remainder by using Euler's 5 function. Okay. If in your examination, if they don't mention any method, you would apply which one is easy method, you can apply that method. Sometimes they may specify the method by using Wilson's theorem or by using Fermat's-Little theorem or by using Euler's theorem. If they mention to solve the problem, you should solve that problem by mentioning the method. So find the remainder when 199 to the power 2020 is divided by 28. So look at the base 199, which is more than the mod value 28. So therefore 199 will be dividing by 28. You can get the remainder 3. Therefore 199 is congruent to 3 under mod 28. So the given dividend 199 to the power 2020 is congruent to 3 power 2020 under mod 28, which will be considered equation 1. Now find phi of 28. Okay, the mod value is 28. So phi of 28. So 28 is 4 sevens are 28. 4 sevens are 28. So 4, since phi is multiplicative function, therefore it can be written as phi of 4 into phi of 7. So phi of 4 means, so 4 is equal to 2 square. So phi of 2 square into phi of 7. So phi of 2 square is equal to 2 square into 1 minus 1 by 2 into phi of 7. So 7 is prime. Therefore phi of 7 is equal to 7 minus 1, that is 6. So 4 into 1 minus 1 by 2, that is 1 by 2 into 6. That equal to 12. So phi of 28 is equal to 12. Then, so what is Euler's theorem? If A is relatively prime to M, then A power phi of M is congruent to 1 under mod M. Here the base value A is 3. The M, so here 3 and 20. 3 is relatively prime to 28. Therefore, by Euler's theorem, we can write 3 power phi of 28, which is congruent to 1. Actually, phi of 28 is 12. So 3 power 12 is congruent to 1 under mod 28. So from equation 1, 199 to the power 2020 is congruent to 3 power 2020 under mod 28. Then now 2020 will be dividing by 12. You can get the quotient is 168 and remainder will be 0. So 2020 can be written as 12 times of 168. So 12 times of 3 power 12 times of 168 can be written as 3 power 12 whole power 168. Okay, into 3 power 4. Okay, actually 12 times of 168 plus 4. The remainder is 4. So 3 power 12 whole power 168 into 3 power 4. So actually 3 power 12 is congruent to 1. Okay, by Euler's theorem. So 1 power 68 into 1 power 168, that is 1 into 3 power 4. 3 power 4 is 81. When 81 is dividing by 28, you can get the remainder 25. So 199 to the power 2020 is congruent to 25 under mod 28. So the required remainder is 25. The required remainder is 25. So when 199 to the power 2020 is divided by 28, so at the time you found the remainder as 25. Okay, so this problem was solved by using Euler's 5 function. Euler's 5 function. Then show that phi of 2 power 2k plus 1 is a square. Show that phi of 2 power 2k plus 1 is a square. Well, we know phi of n, if n is equal to p1 power k1 into p2 power k2 etc. pt power kt, at the time phi of n will be n into 1 minus 1 by p1 into 1 minus 1 by p2 etc. 1 minus 1 by pt. So here 2 power 2k plus 1. So here n is 2 power 2k plus 1 into 1 minus, actually here p1 is 2. Look at the base. Base is 2. So 1 minus 1 by 2. 1 minus 1 by 2 is 1 by 2. So when 2 power k plus 1, 2 power 2k plus 1 is dividing by 2, you can get 2 power 2k. Okay. So 1 2 is reduced. So therefore 2 power 2k, 2 power 2k can be written as 2 power k the whole square. So we proved that phi of 2 power 2k plus phi of 2 power 2k plus 1 is a square. Okay. Since 2 power k the whole square. So therefore phi of 2 power 2k plus 1 is proved to be a square. So derive a formula for phi of PQ where P and Q are twin primes. So you know very well about twin primes. The example for twin primes is 5, 7, 11, 13, 17, 19, which are the twin primes. The difference between twin primes are 2. Okay. If P is a prime, then its twin prime will be P plus 2. Okay. So look at here. P and Q are twin primes. So now we have to derive a formula for phi of PQ. So phi of PQ is equal to, we know very well, phi is a multiplicative function. Therefore, phi of PQ can be expressed as phi of P into phi of Q. That equal to phi of P. For definition of Euler's phi function, phi of P is equal to P minus 1. Q is also a prime. Therefore, phi of Q is equal to Q minus 1. The next step, P minus 1 into P and Q are twin primes. Okay, if P is a prime, then Q will be P plus 2. So replacing Q by P plus 2. So P plus 2 minus 1. That equal to P minus 1 into P plus 1. So P minus 1 into P plus 1 is P square minus 1 square. So phi of PQ is equal to P square minus 1 if P and Q are twin primes. On the next problem, compute phi of 7 factorial. Phi of 7 factorial. So 7 factorial can be expressed as 7 into 6 into 5 into 4 into 3 into 2 into 1. Okay. So then 7 into, so 6 is a composite number. So 6 can be expressed as 2 3s are 6. 2 3s are 6. Then 5 is prime. 4 is a composite number. 4, therefore 4 can be expressed as 2 square, 2 into 2. 3 is a prime, then 2 is a prime. So now 7 into 6 into 5 into 4 into 3 into 2 into 1. Okay, this product can be represented as canonical decomposition, that is phi of 7 into 5 into 3 square into 2 power 4. Okay, into 2 power 4. 7 into 5 into 3 square into 2 power 4. So you know very well the definition of Euler's phi function. Phi of n, if n is equal to p1 power k1 into p2 power k2 etc. pt power kt, at the time the Euler function is defined as phi of n is equal to n into 1 minus 1 by P1 into 1 minus 1 by P2 into 1 minus 1 by P3, etc. 1 minus 1 by Pt. So, and also phi is a multiplicative function. So therefore, phi can be applied on each integer. So phi of 7 into phi of 5 into phi of 3 square into phi of 2 power 4. So phi of 7. So phi of p is equal to p minus 1. So 7 minus 1 is 6. Phi of 5, that equal to 5 minus 1, 4. Then phi of 3 square. Phi of 3 square is equal to 3 square into 1 minus 1 by 3. Then phi of 2 power 4. So 2 power 4 into 1 minus 1 by 2. So this product will be simplified. You can get 1152. So which is the solution, which is the answer of phi of 7 factorial. So phi of 7 factorial is equal to 1152. Then prove that sigma of k of n is multiplicative. Sigma of k of n is multiplicative. Now we know the definition. Capital F of n. The definition of capital F of n is equal to summation d divides n f of d. So capital F of n is multiplicative. Capital F of n is multiplicative since lowercase f is multiplicative. Here, sigma suffix k of n, which means here the function f of n is equal to n power k. So let f of n is equal to n to the power k. So now, apply the formula. So here f of n, here capital F of n is sigma k of n. Here capital F of n is sigma of k of n. That equal to summation d divides n. Therefore here d power k. Since f of n equal to n power k, so f of d will be t power, f of d will be d power k. So it's obviously multiplicative since lowercase f of n, that is n power k, is multiplicative. So obviously sigma of k of n should be multiplicative. Okay. Now the next problem, if n is equal to, n is given 2 power e, 2 power e, find tau of n and sigma of n. So you know very well about the definition of tau and sigma functions. What is the meaning of tau function? Tau of n means the number of devices of n. The number of devices of n. That is tau of n. What is the meaning of sigma of n? Sigma of n means the sum of the devices of the given n, which is the definition of tau and sigma functions. Here n is equal to 2 power e. So tau of n is equal to tau of 2 power e is equal to, look at the base. Here the base is 2. The power is 2 power e. So the base is p. So therefore tau of p is equal to, so tau of, you know the definition, tau of p power k is equal to, tau of p power k is equal to k plus 1. Here k is 2 power e. Here k is 2 power e. Therefore tau of 2 power e is equal to 2 power e plus 1. Then sigma of n. Here n is equal to 2 power e. You know sigma of 2 power e is equal to 2 power, you know, p, sigma of p power k is equal to, sigma of p power k is equal to p power k plus 1 minus 1 divided by p minus 1. That is the formula. Here k value is 2 power e. p is 2. So 2 power e plus 1 minus 1 whole divided by 2 minus 1. So 2 minus 1, the denominator 2 minus 1 is 1 now. So therefore 2 power e plus 1. Actually in the power k value is 2 power e. 1 is added with k, which means 1 is added with 2 power e. So 2 power e plus 1 minus 1. That is sigma of 2 power e. Any clarification in this problem? Next problem, show that this problem is given in your assignment problem. So many of you are having the doubt in this problem. That's why I will explain the solution. Show that n power 4 plus 2n cube plus n square is congruent to 0 mod 4 for any positive integer n. Okay. So this problem will be proved by using method of induction. So you know the procedure of method of induction. The basic values, for example, the basic integer 0, 1, 2, 3. Okay. In this case, the given linear congruence is 2. Okay. Just simply putting n equal 0 or n equal to 1 or n equal to 2, this linear congruence is satisfied. The basic integer values. Then for the k values, assume for n equal to k, this linear congruence is true. Okay. Then we are going to prove for n equal to k plus 1 case. We are going to prove for n equal to k plus 1. Okay. If you prove for the case k plus 1, if you prove for n equal to k plus 1, then this linear congruence is true for any positive integer n. Okay. So it is the procedure for method of induction. Okay. For the basic value, for putting n equal to 0, either 0 or 1 or equal to 2. Here I have taken n is equal to 1, put n equal to 1. So 1 power 4, 1, 2 into 1 cube, that is 1, then 1 square 1. So the summation is 4. So obviously 4 is congruent to 0 under mod 4. Since 4 is dividing by the mod value 4, you can get the remainder 0. So 4 is congruent to 0 mod 4. So this linear congruence is true for the basic integer value n equal to 1. Okay. Assume this linear congruence is true for an arbitrary integer k greater than or equal to 0. Okay. So therefore, k power 4 plus 2k cube plus k square is congruent to 0 under mod 4. Okay. For n equal to k, this linear congruence is true. Then we are going to prove for n equal to k plus 1 case. Okay, if you take n equal to k plus 1 case. So to prove that n power 4 plus 2n cube plus n square is congruent to 0 under mod 4 for any positive integer k plus 1. Okay. So it can be proved that look at the left hand side of linear congruence, replacing n by k plus 1, you can get k plus 1 the whole power 4 plus 2 times of k plus 1 the whole cube plus k plus 1 the whole square, which is congruent to. So k plus 1 to the power 4, which can be expanded, that is k power 4 plus 4 into k cube into 1 plus 6 into k square into 1 square plus 4 into k into 1 cube plus 1 power 4. Okay, so k power 4 plus 4k cube plus 6k square plus 4k plus 1, which is the expansion of k plus 1 to the power 4. Then plus 2 times of k plus 1 whole cube. K plus 1 whole cube, which will be expanded, that is k cube plus 3k square plus 3k plus 1.
But you know the formula a plus b the whole cube. A cube plus 3a square b plus 3ab square plus b cube. Then the last one k plus 1 the whole square. So which is the form of algebraic identity a plus b the whole square. That is a square plus 2ab plus b square. Here in the place of a, k in the place of b is 1. So now which can be simplified, actually k power 4, then 4 cube will be added with k power 4, then 4 cube plus 2k cube, that is 6k cube, then 6k square plus 6k square, then again single k square, that equal to 13k square, then 4k plus 6k plus 2k, that is 12k, then 1 plus 2 plus 1, that is 4. So under mod 4, so look at the coefficients of k power 4, k cube, k square, k, then constant term. If if the coefficient of k power 4 or k cube or k square or k, then constant term, which are any integer more than the mod value, then that coefficients will be divided by 4. You can replace its congruent to the remainder. So here coefficient of k power 4, that is 1. 1 is less than the mod value. Okay. So keep 1 as it is 1 into k power 4, k power 4. Then coefficient of k cube, that is 6. 6 is more than the mod value. Then 6 will be divided by 4. You can get the remainder 2. So 6 is congruent to 2. So 2 times of k cube. Then 13 k square. 13 is more than the mod value. So when 13 is dividing by 4, you can get the remainder 1. So 13 is congruent to 1. So 1 into k square. Then 12. When 12 is dividing by the mod value 4, you can get the remainder 0. So 12 is congruent to 0. So 0 into k, again 4. When 4 is dividing by 4, you can get the remainder 4. So 4 is congruent to 0. So you can get k power 4 plus 2k square plus k square. So already for the case k, okay, we have assumed for the case k, this linear congruence is true, which means k power 4 plus 2k cube plus k square is congruent to 0 under 4 under mod value 4. Therefore, here k power 4 plus 2k cube plus k square is congruent to 0 under mod 4. So, by method of induction, we proved that the given linear congruence n power 4 plus 2n cube plus n square is congruent to 0 under mod 4 for any positive integer n. So this question was asked in your assignment 2, okay, which is the 6th problem for your assignment 2. So this problem, so many students have the having the doubt how to solve this problem. That's why I have explained. So unit 5, unit 5 is completed. From the next classes, unit 1 will be started. So if you have any doubt, you can ask us. We are eagerly waiting to clarify your doubts. And most of the students didn't complete the assignment 2. Okay. So unit 3 was completed. So all of you complete the unit 2 assignment. Okay. Unit 2 means here unit 4. Okay. The second assignment. So already the deadline was so you are beyond the deadline. So by tomorrow you have to complete the assignment 2. So thank you, students.